Hello and welcome to ECMath. Today we're going to look at the idea of the inverse of a function. Have you ever gone to school? Well, I hope you have. Think about the steps you might take. You get up, you get out of bed, you leave the front door, you go down the stairs, you walk to the train, you take the train, you get to school, you go to class. Now say class is over, you want to go home. What do? You're going to do the exact same steps in the complete opposite order. You leave the school. You get on the train. You take the train. You walk back to your house. You go up the stairs, in the door, and get right back in bed. And you're exactly back to where you started. If you understand this key idea of repeating the same steps but in the opposite order, then you already understand the idea of taking the inverse of a function. Some notation stuff. Before you watch this video, you should be really confident about how you use function notation, be able to compose functions f of g of x. That's the video in section 1.7. And you should also be pretty confident in your techniques of using algebra to solve equations. So getting right into it, we're going to consider two functions, f of x and g of x. And right now, we don't know what their equations are. We're being about as general as we can. I'll say if f composed with g of x is equal to x, and if g composed with f of x is also equal to x, maybe add a little star that says for all x in the domain of f and g respectively, because this doesn't work if we're plugging in x that gives you undefined values, of course, then g is considered the inverse of f, and we can call it f inverse of x with that little -1 that's not an exponent, and it would be true that f inverse of f of x equals x, and f of f inverse of x would also equal x. So this definition is, a little vague, it's a little mathematical, but it's capturing the essential idea that if you have two things you're doing to a variable, you do one thing, then you do the other thing, and you get back to where you started, and you do it in the other order, and you also get back to where you started, then those two things must undo each other in some way, and we consider them inverses of each other. First example. So one of the things you might be asked to look at is be given two functions and have to decide if those two functions are inverses of each other or not. That is, do the steps of one function undo the steps of the other function? And you might be able to look at this and sort of think through it or articulate whether you think these are inverses, but the best way is actually just to check. And if I ask you to do this question, I'm asking you to do the following steps. We need to compute f of g of x, and we need to compute g of f of x. And at the very end, if they're both inverses, we should get, as a result, x on both sides. I'm going to say question mark, because we still have to do the algebra. So let's pause. This is where I said we need to use our function composition. Let's do that algebra and see what we get. So when we do this algebra both ways, we do in fact get x from both directions of the calculation. So it is fair to say that f and g are inverses, and we could replace, and instead of calling this g of x, we could call this f inverse of x. Or, if we're feeling saucy, we could cross out f and call this g inverse of x as well. Now, one or the other, not both, of course. And that's how you, in general, will check or prove that f and g are inverses. Compose them with each other in both directions, and confirm that both sides give you an x. Here's a slightly more interesting example of two functions that may or may not be inverses that we have to check. And this one might be a little harder for you to just inspect and see. So we have 3 over x plus 2 and 3 over x minus 2. By the way, if you see my little note, the first could be thought of as a horizontal shift of the function 3 over x, and the second could be thought of as a vertical shift of the same function 3 over x down. We'll learn to graph the function 3 over x in the next chapter, and then you might be able to come back to this section and see if it makes the graphs of these kind of confirm what we verify about inverses. So we'll first sort of set up the page. I'm going to compute f composed with g of x, and g composed with f of x. And hopefully we get the same thing, and that thing is x. All right, so we simplified in both directions, and f composed with g gave us x, and g composed with f gave us x. For g composed with f especially, we kind of had to do a complex fraction, being careful with our denominators. For both of these, by the way, that single 3 on top is really helpful to think about that as like 3 over 1, so that when you do the reciprocals, you get everything in the right place. If you were working this out on your own and you didn't get x in both ways, my guess is that something went wrong with the fractions, and you should go ahead and check your fraction math. But these should give you inverse. These should be inverses of each other because you get x in both directions. All right, so let's go ahead on to a third example, and this one might be a little bit tricky because if you look at these two functions, you might just immediately say, oh yeah, of course they're inverses of each other. But remember, the mathematical definition of inverse is not necessarily the same as the English language definition of the word inverse. So to check mathematically, we need to compute f composed with g and g composed with f and see what we get. So f composed with g. Okay, so already that's a pretty discouraging result. When you do the fractions correctly, the 4's do cross out, but you don't get x, you get 1 over x. We should get just x if these two are inverses. Let's check the other direction as well. And it turns out again that when you do the fractions correctly, for this one, think about the top as 4 over 1 divided by x over 4. You do that reciprocal. You get 16 divided by x. The 4's didn't even cross out. And this is super, super wrong because not only are those not equal, they're also not equal to x, which is what we should get if they're indeed inverses. So although these two functions are reciprocals of each other, they are not inverses of each other. I made a note of that right here. So important language note. The -1 that you see in inverse notation is not an exponent and does not mean the same thing as reciprocal. The idea of inverse is sort of broader than the idea of reciprocal. And yes, when I write 1/2 to the -1, I do mean that you take the reciprocal of that fraction and you get 2 over 1. But that's not the same as function inverse. Those are completely different ideas. This is actually what we call the multiplicative inverse, because 1/2 times 2 over 1 is equal to 1, but that's different than the function inverse. So multiplicative inverse is reciprocal. Function inverse is what we're doing in this video. So what if you aren't given two functions? What if you're just given one function and asked to find its inverse? The steps to finding an inverse are pretty simple. There are 4 of them. And the 2 key steps are in the middle. So you're first going to replace f of x with just a y. Then we're going to exchange x with y. And that's the step that actually creates the inverse. And then we're going to resolve it for y so that we can create it as a function. And then we'll rewrite it in function notation, replacing y with f inverse of x. So we're going to switch x and y, solve for y, write it as f inverse. Let's do it in an example. All right, ready to go. So we have f of x equals 10x plus 2. So the first thing I'm going to do is rewrite the function as y equals 10x plus 2. Then I'm going to do the second step, interchange x and y. I'm going to switch colors here to represent that I've now created the actual inverse relationship. We'll switch to purple. X is equal to 10y plus 2. So I'm switching like the start and the end. We're saying, all right, instead of going from home to school, you're now going from school back to your house. Now I have to solve this again for y to actually find the route to my house. And I'm going to use good, valid algebra steps. There's a couple ways to do this, but they'll all give you the same result in the end. Let's subtract 2 from both sides. Get x minus 2 is equal to 10y. And then we'll divide both sides by 10 and get x minus 2 all over 10 is equal to y. You can leave it like this, or you could write it as x over 10 minus 2 over 10 is 1/5 is equal to y. Either of those are fine. And then the last step, I'll do it over here, is to write it as, since we've solved for y now, but I just added the y in the start, I'll write this as f inverse of x is equal to, and I'm actually going to use this first version because I like it better, x minus 2 all over 10. Not so bad. It's just kind of linear equation solving. If you want to check your work, you could, of course, compose your answer with the original and see if you get x. And if you're doing it as a check, you probably don't need to do it both ways. You can just check one direction. So I'll do f inverse of f of x and just see what I get. So then f is the inside function, so I have 10x plus 2 in the place where I had the x, minus 2 over 10. Sorry, I get 10x, 2's cancel out, over 10, and I do get x. And I'm pretty confident that if I did it the other way, I'd also get x, and I'm just doing this as a check, so I don't really need to check the other direction, f composed with f inverse. Here's something a little spicier. F of x is equal to 2x cubed plus 8. So first step, rewrite it as y equals 2x cubed plus 8. And we need to first switch x with y. So I'm going to switch x and y, changing colors again to indicate that I've now created the inverse relationship. And now I need to solve this for y so that I can describe it as a true, real function. I need to get y alone. I'm going to have to take a cube root to get rid of that cube, but before I can, I need to get the y cubed all alone. So we have to take away 8 first. And divide by 2 first. Now I can take the cube root, and we just do the cube root of both sides. And I'll rewrite that over here in function notation as f inverse of x is equal to the cube root of x minus 8 over 2. I will leave it as an exercise to you, the viewer, to compute f inverse of f of x and see if we've done this correctly, or, f of f inverse of x. But if we have done this correctly, both of these should give you x as the result. They should undo the actions of each other. For the last example, I didn't want to end this video without closing the loop on the function that we saw above where we did not have an inverse, right? We computed f of x and f of g of x and g of f of x and did not get the same thing. So this is one of our functions, was 4 over x. Now that we know how to actually correctly compute an inverse, let's compute the inverse function of f of x equals 4 over x. First step, write it as y equals 4 over x. Second step, we're going to interchange x and y, switching colors. So I'll have x equals 4 over y. Now I need to solve this again for y, but y over here is on the bottom of a fraction. So to clear that out, let's multiply both sides by y and rewrite. So we have yx equals 4. And those would reduce out. Now I need to divide both sides by x and get y is equal to 4 over x. Well, I've solved for y, so the only thing left to really do is write this in function notation. F inverse of x is equal to 4 over x. But an interesting thing has happened. That was actually the same as the original function. So we have now uncovered a function that is its own inverse. How neat is that? And let's actually check that. So f of f inverse of x, and since they're the same, I'm really just checking both directions in one step. So if I have f of x is 4 over x, so it's 4 over, and then I put the inverse equation, 4 over x. Well, that 4 on top is really like 4 over 1, so this is really like 4 over 1 times x over 4. 4's reduce out, and you get x over 1. So it is actually true that the inverse function of 4 over x is 4 over x. And that's cool, isn't it? It's also interesting, again, going back to that idea that inverse does not mean reciprocal always. Inverse means inverse using this definition, and we can find it using this procedure. I hope this video hasn't been too bad. Inverses can be sort of theoretically difficult and complicated, but the actual algebra steps are pretty simple, and that's what we wanted you to cover in this video. Please go ahead and take a break now, and then stay tuned for the next video, where we'll get into more of the theory of inverses, which is important as well. See you next time.